Thank you. Thank you for inviting me. And so I'm going to tell you about BKL dynamics. So the bigger picture are singularities. Singularities, we all, at least many of us, believe are quite interesting. At the singularity, you might hope to see, you might be forced to confront the microscopic description of whatever your theory is. It's a good time to ask this question. There's been a lot of progress in the last couple of months, a couple of very nice papers about probing the singularity from the boundary. This talk is not really going to be a boundary-anchored talk. Nonetheless, these singularities are things you might hope to access from the boundary. And now we have, I think, some rather nice ideas for how to do, well, other people have had some rather nice ideas for how to do that. Of course, this goes back a long way to the works of Schenker and Honglu and others. Now, if you want to probe the singularities, the question is, well, which singularity should you be probing? And almost all work in this context uses something like a Schwarzschild singularity. But in fact, even though the outside of black holes are quite robust things, okay, if things fall into a black hole, they get a little bit bigger, but they settle down back to Schwarzschild. That isn't true for the singularity, okay? And so the Schwarzschild singularity is highly unstable. Another way to say that, it's a highly non-generic space-like singularity. And an easy way, I mean, this is a mathematical statement, but a very easy way. You can see this that we did a few years ago. If you deform the boundary of your ADS or your thermal field double, so I've only put one arrow here, but I'm deforming both sides by some relevant operator, that the black hole space-time will change. And certainly the singularity will not look like the Schwarzschild singularity anymore. In the simplest case of just a time and space-independent scalar field, it will get deformed into a more general set of scaling solutions with power law metric components towards a singularity called a Kasner universe, of which Schwarzschild is a special case. Okay, and so in particular as an exponent, this is how the time component of the metric is going as a function of the proper time to the singularity, and there's some exponent that appears here that is equal to 1/3 for Schwarzschild, but in general will take a different value. However, this is a rather mild deformation of the Schwarzschild singularity. And in fact, as I'll describe in a minute, what BKL argued many decades ago is in fact the properly generic behavior is much richer than this. And something that happens, so this is, you get one scaling Kasner universe, but in fact, the generic behavior is expected to be something where there's a whole chaotic sequence. So this is, again, sort of the approach to the singularity. These are the metric components. This is a doubly log graph, okay, because a lot of time is passing, and you get this infinite sequence. Each of these lines is a Kasner universe, and there's a series of bounces, as I'll describe in a minute, okay? And now if you want to actually make these plots, you, again, don't want to go all the way to BKL, which, as I'll describe, is a bit complicated, but there are various mini superspace models where you still have a certain amount of homogeneity, and those are the models that you can solve very explicitly and see this chaotic behavior that is expected to be, as I'll describe, more generic. And so we had an explicit model of this a few years ago, embedded into a ADS black hole. Okay, so there are ADS black holes where the approach to the singularity looks something like this. Okay, so now I want to review what the BKL ansatz or singularity is. So this is not the way BKL did it, but I think the fastest route to understand what's going on is from a Hamiltonian formulation of GR. So you split up your space-time, you pick a time, you split it up into slices, and then let's start in 4 dimensions. And so on each slice, you have a 3 metric, okay? And so what is the 3 metric is a symmetric 3x3 tensor. So it has six degrees of freedom, okay? So there's 6 degrees of freedom on the slice. You can roughly think of it as 3 diagonal components and then sort of 3 off-diagonal components of the metric. There's a particularly nice way of parameterizing it. It's called an Iwasawa decomposition, which I will not go into the details of, but essentially you have these betas are the scale factors of the metric on the slice locally, the functions of space. And these are certain nice choices of one forms. In particular, they have the property that they don't contribute to the determinant. Okay, so the overall volume of the slice is just the exponential of the sum of these betas. Okay, these theta ones are sort of some Gram-Schmidt orthogonal basis. With this choice, what happens? This is just it's not an assumption, okay? It's just a way of parameterizing a 3-metric. The Hamiltonian constraint, which, as you know, is one of Einstein's equations and is a very, very important one, schematically, so dropping all the indices, looks like this. So it's a Hamiltonian formalism, right? So there are now fields and their momenta, right? So there are 6 fields and 6 momenta at each point in space. And so there's a momentum, this is a pi momentum squared for the scale factors. There's a momentum squared for sort of off-diagonal terms. And then this is the Ricci, the three Ricci scalar of the 3-metric. Now, multiplying the off-diagonal terms and the Ricci scalar is the exponential of differences of these scale factors, right? It's like a gxx times gyy inverse. Okay, you get the inverses, products of these scale factors, multiplying these. And the other thing I'm highlighting in this formula is that the Ricci scalar term is the only place where spatial gradients of these terms appear. Okay, this is pointwise in space on the slice, and all the spatial gradients appear in this term here. That was very quick. If you want a leisurely and clear review, you can look at this book by Belinsky and Hartnoll. There is a shortage of clear expositions of this material, but this is not a bad place to look. Okay, and so the BKL limit, you can think of as it's a limit of this equation that I just wrote. Okay, so let me maybe, so what does this look like? This looks like a dynamical system where you have a particle moving in some exponential potentials. Okay, and the BKL limit is a limit where these exponential potentials are taken to be very steep and they become infinite barriers. Okay, and so the idea is we want to zoom in on the singularity, and to do that, you should take these betas to either plus or minus infinity. Okay, naively, the volume going to 0 is where the betas would go to plus infinity. But as you know from Schwarzschild, when you go to the singularity, 2 of the dimensions collapse, but one of them expands. Okay, so in general, you have to let these betas go to plus or minus infinity toward the singularity. And so you're going to take this limit such that these differences go to plus or minus infinity, which is the generic thing for the differences to do. And so you can think of this as zooming in on the small volume region of phase space. In that limit, the Hamiltonian constraint becomes generically something like this. So these are the betas, right? This term, which I've now written out more carefully with all the indices, becomes this term. And these terms, both this one and this one, just become infinite step functions because this e to the delta betas either goes to 0 or infinity, depending on whether the delta betas go to minus or plus infinity. There's a big simplification here because when something is 0 or infinity, you don't care about what's multiplying it, okay, in either case. And so the coefficients, that they turn out to be positive. It's a non-trivial thing. But the idea is that their value doesn't matter. And so I've just dropped them here because these things are either 0 or infinity. And in particular, all of the coupling between different points in space, which was hidden here, has also vanished in this limit, okay? And so in this BKL limit, the evolution of each point in space decouples, okay? Another thing that happens in this limit is that the pi thetas have also dropped out, and this manifests itself in the theta variables freezing, okay? So within this BKL scenario, what you end up with close to the singularity is a dynamical system for the 3 scale factors at each point in space evolving independently according to this dynamics, which is sort of going to be free dynamics with some infinite barriers, okay? So there are 2 factors here. There's the infinite barriers and there's the decoupling. Okay, the infinite barriers, you can see this emergence of the infinite barriers by doing some sort of mini superspace simple homogeneous models. That's what's happening here. The decoupling of points, I think, is less hard to prove. Sorry, it's harder to prove. Some numerical evidence in its favor comes from this paper. So this is a dimensionally reduced case where the non-trivial x dependence is only in one of the 3 directions. And what you're seeing here is a slice evolved in time, and the fact that it's becoming more inhomogeneous is the fact that the different points are decoupling, right? When different points don't talk to each other, you're not getting penalized for having spatial gradients, and that naturally leads to a very inhomogeneous interior. Okay, so the rest of the talk is going to be about this system. Okay, so on this system, you can do a very simple change of variables. I've just written it here so that you see that it's simple. This is what you would do to go to a Milnor universe, to write Minkowski space in these Milne coordinates. So it's a familiar to some transformation. And under this transformation, something very, very nice happens. So so now instead of beta 1, beta 2, beta 3, I've got tau, x, and y. Okay, it's just a change of variables. The Hamiltonian constraint, I've now dropped the thetas in the regime where the step functions are 0, so in the allowed regime. You can write it like this. So pi tau squared is y squared, pi x squared, pi y squared. This is the Hamiltonian of a particle moving on a two-dimensional hyperbolic space. Okay? And these infinite walls that were written in terms of betas, when you write them in, they don't depend on tau. When you write them in terms of x and y, they restrict x to this strip, and x squared plus y squared has to be bigger than 1. So as many of you will know, what this defines is precisely half of the fundamental domain of SL2Z acting on the upper half plane. Okay? So again, the picture is like this. Now, of course, here we have the Hamiltonian constraint. So in the spirit of the previous talk, the way we deal with this Hamiltonian constraint is to think about it relationally, right? And you should think about this as a relationship between saying if you evolve tau, which is not quite the volume of the spatial slice, but you can think of that as a proxy for it. So as you evolve in the volume, the shape of the universe, which is defined by these at each point in space, evolves in this correlated way. Okay, because this is at each point in space. So you can think of having a little drop of water right here. As you go to the singularity, that drop of water starts deforming, and that's what's described by this evolution. Okay, so Einstein's equations, according to evolve the shape of the universe of the shape of a drop of water as a function of time to the singularity in this way. What we've mapped that to, we've shown this is equal to a billiard dynamics in half of the fundamental domain of SL2Z, which is given by this sequence of bounces. And so these bounces here, each one corresponds to a Kasner epoch. And so these lines here are the same as these lines here. Okay, right? The metric undergoes a series of transformations, which can be mapped mathematically to a hyperbolic billiard. Okay, and so I think it's certainly not understood by me. I'm not sure by anybody, but it's pretty interesting. This SL2Z is just coming out by itself. Okay, we're not notorious something is being put in. Just to show you that this is not special to 4 dimensions. So, for example, in 5 dimensions, 5-dimensional pure gravity, you can do the same thing. And now, because there's an extra metric component, there are 4 betas instead of 3. One combination you think of as the clock, and then you have a 3-dimensional motion, which turns out to unfold now in 3-dimensional hyperbolic space. And the billiard domain that you get is a fundamental domain of now SL2, not over Z, but over some 2-dimensional integers. Okay, this is a discrete subgroup of SL2C, and the integers that appear in pure gravity are the Eisenstein integers, which is a triangular lattice. Right, the Eisenstein integers are a triangular lattice inside C. Right, just the same way that Z is inside R, right? So SL2Z is a subgroup of SL2R. SL2 of these Eisenstein integers is a subgroup of SL2C, and this is roughly what the fundamental domain looks like. For importance later, you can factorize these integers amid a prime factorization. Okay, so any one of the points on this triangular lattice, you can decompose it as a product of some prime integers. So this is a picture in the complex plane of the Eisenstein primes. This will come back later. And so this group is an example of a Euclidean-Bianchi group, and it has S, right, which is just like SL2Z. Now there are 2 translations because you have a 2-dimensional sort of base here, and there's also a discrete rotation in that base. Okay, so it's very similar to SL2Z, just a little bit bigger. What about high dimensions? So you can keep going up. And so the domain that you get depends on the matter content, and it's been extensively studied in supergravity theories, particularly by Damour, Hartnoll, Nicolai, in a whole series of papers. Particularly interesting dimensions are 4, 5, 7, and 11. So I've talked about 4 and 5, and we saw we had discrete subgroups of SL2R, SL2C. And so in 7 dimensions, you get sort of quaternionic modular groups. And in 11 dimensions, you get octonionic modular groups, whatever those are. And so I think one interesting question here that certainly Nikolai has been interested in for a long time is whether this octonionic modular symmetry is somehow a clue about the degrees of freedom in M theory, right? It's arising in this near singularity regime. But because that's a very subtle object, our approach has been, so we want to try to take these symmetries as starting points and see if they tell us something about the holographic dual of these singularities. We'd love to do that in M theory, but to work up, we're going to start in R, and then that was this first paper with my student Ming Yang. A second paper with Marine, who's a postdoc in Cambridge, and Ming Yang. We looked at the case of C, and we're now thinking about the quaternionic case. So indeed, there's a lot of interesting physics here, but we've ended up on a bit of a mathematical detour that's been quite fun. Okay, so just to recap so far. So close to the BKL singularity, each point in space evolves independently, and space at each point follows a hyperbolic billiard dynamics in a modular domain. At a classical level, the structure, I think, would be a very interesting target for these boundary probes that I mentioned at the beginning. But the rest of this talk, I'm going to take more of a purely interior perspective. And I'm going to tell you that the sort of semi-classical Wheeler-DeWitt wave functions in this billiard domain have some interesting structure that might suggest a dual formulation, but this would not be a boundary dual. This would be more of a sort of DSCFT-like kind of, or intrinsically interior dual. Okay, good. So with that in mind, I want to now thinking about the interior, the quantum state, the semi-classical quantum state of gravity as we're getting close to singularities. Obviously, Einstein gravity is going to break down as you get too close to the singularity, and the question is whether this structure that is emerging is something that survives in that regime or not. Okay, good. So the Wheeler-DeWitt quantization just means I take that constraint equation that I wrote before, and I promote all of the pi's to operators. Just to be completely clear, this is not supposed to be a microscopic theory of quantum gravity, but some semi-classical quantization of the gravitational field. Now, a crucial thing is that tau doesn't appear explicitly in the Hamiltonian, right? So we had this is the quantity I'm quantizing. There's no tau here, and so it's natural there's an emergent time translation invariance in superspace in this regime. So we can expand the wave functions in sort of plane waves in this tau direction. Remember, tau is something like the volume of the spatial slice, and then we get a bunch of modes. We plug that, of course, there are also ordering ambiguities when you do this quantization. There's a natural ordering, but in the semi-classical regime, it should not be too important. So with the natural ordering, this was the Hamiltonian, right? The billiard Hamiltonian. And so you get the Laplacian on hyperbolic space. This is what the mode, so K is the mode number. And then there's this shift by a quarter that, again, not too important to leading order at large epsilon. And so there are eigenmodes. So that the Wheeler-DeWitt equation leads you to a natural basis of eigenmodes, which are Laplacian eigenstates on this domain. Okay? So these define odd orthomorphic forms of SL2Z. Okay? They're odd because the Dirichlet boundary conditions means they vanish on the boundary. And so if you want to extend them to the full space, you can use SL2Z transformations to unfold them, but you need to use a reflection to map it across that domain to the other side. And it has to transform with a minus sign under that reflection so that it vanishes along this line. Okay? So if this was the classical motion of the universe, this bouncing motion of the universe close to singularity, the semi-classical quantum version is a mass waveform in SL2Z. Okay? Good. Because it's in the odd sector, the spectrum is discrete. There's also the Eisenstein, the non-holomorphic Eisenstein series, but that is even and does not appear here. So it turns out solutions to this equation have been very widely studied in the 90s. and they form the domain of what's called arithmetic quantum chaos. So hyperbolic billiards is the canonical example of a chaotic system, and therefore of a quantum chaotic system. However, what was realized in the 90s is that when you have these special domains with certain number theoretic properties, the chaos is not quite the standard one, and that's why it's called arithmetic quantum chaos. So in the remainder, I want to talk about these wave functions. Yeah, good. Okay, so this is the most technical slide, but it's not too difficult. So if you give this equation to an undergraduate, okay, they're quite capable of solving it. It's not so different from things that you see in undergraduate quantum mechanics. What's the first thing that hopefully they're going to do? Well, they're going to say, well, x doesn't appear here. I need it to vanish at 0.5. And so I should Fourier expand in x, right? So I'm going to take this mode, and I'm going to Fourier expand it. I'm going to separate variables. This sign vanishes at 0.5. I get a bunch of Fourier coefficients. And when you separate variables and you impose that it vanishes at the cusp in the y direction, you get some Bessel function here. Okay, very simple. It turns out there's a lot of structure in these coefficients. And to make that more useful to you, you need to do one step, which is to Mellin transform this expression. Now, one way that you might want to think about that is that if you unfold this in the upper half plane, you can think of that as a state of a quantum mechanics on H2, which is a conformal quantum mechanics, and also has a dilatation generator, right? And so this is the state in the X translation basis, but instead we can express it in a dilatation basis, right? So if we think of, these are the coordinates in the upper half plane. If we go to polar coordinates, the dilatation is just rho dd rho, okay? And the eigenstates of the dilatation operator are these sort of plane wave power law states. So the Mellin transform is just taking this wave function, and instead of expressing it in a translation X basis, we want to express it in a dilatation basis. Okay, they're like the plane wave states. When you do that, the nice thing is, look, because here y becomes rho cosine theta, x becomes rho sine theta, and you integrate over rho, you can rescale rho and move these ends out to the front. And so you can package all the end dependents together when you do this integral. Okay, that's why it's a good thing to do. So all the n dependent, the sum over n, is all incorporated into this c function, which I'll define in a second. And then the theta dependent separates into some hypergeometric function, which is boring for our present purposes. And so again, this Mellin transform of the same wave function in the dilatation basis gets packaged into this c function, which again is something boring, meaning some gamma functions, times this sum. Okay, and so once again, the point of doing this Mellin transform, which you can read about in this paper, is to separate out, to take all these Fourier coefficients and group them into this thing, which is now a Dirichlet series. So the Mellin transform of the wave function of the universe is proportional to this Dirichlet series. Okay. So this is a very interesting mathematical object called an L function. Right. Now, just to contextualize things, L functions are generalizations of the Riemann zeta function. Okay, that's their reason for being, at least originally. So let me just quickly remind you about the Riemann zeta, two things about the Riemann zeta function. So that's this object invented by Riemann to prove things about prime numbers, but is an incredibly physical object, and it has at least two Hamiltonians hiding in it. Okay. So as you probably, many of you know, if you analytically continue this function into the S plane, there are a series of non-trivial zeros along this axis. These are not, I'm not going to spend a lot of time talking about that today, but these zeros are very random matrix statistics, and quite possibly the eigenvalues of some chaotic Hamiltonian. In this domain, this is closer to what Riemann did, this sum can be written as this product over prime numbers. It's very easy to see this. Essentially, you expand out, you do a geometric series for this, you get a series of sums for different primes, and when you multiply out all the factors, the different possible prime decompositions of n appear as all of the terms. So if I had a blackboard, I could do this in a couple of minutes, but I won't do that now. But I'm saying going from here to here is elementary. It's elementary. Okay. Now, where in physics is a sum equal to a product? Well, it's whenever you have a partition function of non-interacting particles, right? The partition function of the non-interacting is a trace, but it becomes the product of the non-interacting, of the single particle partition functions. So that's exactly, or said differently, for a free theory, the trace is also a determinant, which is a product, yeah? And not only that, but this product, this is precisely a Bose-Einstein factor here, right? You write this as e to the minus s log p. This is the Bose-Einstein factor of an oscillator with energy log p. Okay, so in fact, this Riemann zeta function can be written as a trace of e to the minus sh, where the Hamiltonian is for a sum for every prime. You have a harmonic oscillator with energy log p. Okay, and so this has been known to many people for a long time, but Bernard-Julia called this a Primon gas. Okay, so the Riemann zeta function is the partition function of a fairly nice physical system. All right. So the whole point about L functions is that they have all the same properties as the Riemann zeta function. They have non-trivial zeros, they have a reflection formula, and they also have an Euler product expansion. So let me just tell you how that goes. And it has to do with these Fourier coefficients. So it turns out you can prove, again, not a posteriori, not difficult, okay, not fancy mathematics. You can prove it in a page, that the coefficients are not all independent. And in fact, all the coefficients can be written in terms of the prime coefficients, prime Fourier coefficients. So in particular, if m and n are co-prime, then the coefficients of their product is the product of the coefficients. So for example, the 18th Fourier coefficient is the 9th Fourier coefficient times the 2nd Fourier coefficient, okay, for every basis. This leaves the case, so using that, you can separate things into primes, such as 2. Now 9 is a prime squared, okay, so that's a slightly special case, but for that, there's also a recursion relation that relates, for example, C of 3 squared to C of 3 squared, but you have to have this minus 1, and this is all in a convention where in a normalization, where the first Fourier coefficient is set to 1. Okay. Again, I won't go through it, but it's not difficult. That using these relationships, the Dirichlet series can again be written as a product. Okay, you do it in 2 steps. Basically, the first step, you use this Hecke relation, and the second step, you use this Hecke relation, and you get this thing here. Okay, so this L function can be written as a product. It's a little bit more complicated than the Riemann, right? So the Riemann zeta case, you didn't have that term, and this was minus s, but note that only the prime coefficients appear. And so that's another nice reason to write the wave function and to isolate all the Fourier coefficients into this L function, is you can then use that to only have the prime Fourier coefficients appearing. Okay. Now this perhaps doesn't quite as much look like a Bose-Einstein factor. So the objective now is to write this as a trace. Okay. But in fact it is. So something called the Ramanujan conjecture states that all of these coefficients are less than 2, have magnitude less than 2. And so if the coefficients have magnitude less than 2, it's natural to write them as 2 times the cosine of some angles. If you do that in the previous formula, you can factorize it, and now our L function becomes a product over primes of this term times this term, right? Where this phase and this phase combine to form a cosine, which gives you the CP term on the previous slide. And this is now recognizable as a partition function again, but with these extra phases. Okay, so again, the energy is log p, and because there are 2 of these, you have an oscillator for every prime and an anti-oscillator. So they have the same energy log p, but they have opposite charge. Okay, and these theta p's appear, again, remember k is the label for each, there's many energy levels. Each one of them has a collection of these theta p's, appear as a sort of an imaginary chemical potential for every p, right? So there's a whole bunch, there's a U1 for every prime, right? It's a complex oscillator for every prime. And what you have to do is stick in an imaginary chemical potential for the primes. Okay, so what that means is that the Wheeler-DeWitt wave functions, the quantization of Einstein gravity close to singularity, semi-classically, are given by the inverse Mellin transform to go back of this partition function, where you have to analytically continue it, okay? Because the Euler product is defined here, the wave function was actually defined along this axis. Okay, so there is an analytic continuation involved that would be nice to get rid of. Yeah, 5, right? Yeah. Good. Right, so once again, yeah, the wave functions are essentially a Mellon transform of an associated oscillator partition function. Okay. I think this is a pretty interesting, so in general, wave functions and partition functions are different beasts, right? One is a state in the Hilbert space on a certain basis. The other one is a sum over all the states, a weighted sum over states in the Hilbert space. And this kind of correspondence is reminiscent of connections between Chern-Simons theory with CFT partition functions, or in fact the DS-CFT correspondence, which is again supposed to be a connection between states and partition functions. The last slide with content is quite interesting. You can also do this for the 5-dimensional pure gravity. So there we had SL2C. Now SL2C has a dilatation, but it also has a rotation that commutes the dilatation, right? It's basically the rotations in the base that I had before. And so you can express your Wheeler-DeWitt wave function in a basis of simultaneous dilatation and angular momentum eigenstates, right? So I have a Mellon transform in the rho direction to give you a T, but I also do a Fourier series in the rotation, and so that gives me a label N. And the L functions that you get in this case are called Hecke. They have an extra so-called Grossen character here. So now we have the sum, not the L function is a sum of all of the Eisenstein integers with the Fourier coefficients. Now these Eisenstein integers are complex, so they have a norm but also a phase, right? And so the S, the dilatation eigenvalue relates to the norm, and this rotation eigenvalue relates to the phase of the complex integer. There are Hecke relations for these coefficients, and that again implies that this wave function can be expressed as a partition function. And I just want to flash a formula in case it means something to anybody. At the individual, right? So this L can again be written as a product over the Eisenstein primes. Okay, so these P's are complex prime numbers. And it looks intriguingly CFT-like, okay, in the sense that the trace are these two factors from the oscillators and the anti-oscillators. And so for every complex prime, there's an oscillator and an anti-oscillator. They have opposite charges, okay? And the charge depends on these angles and also the log of this norm. And you can write as a trace of 1 over the complex prime to this operator times 1 over the complex conjugate of that prime to this operator. So it looks a little bit like trace QL0 bar. I mean, it's not, but where Q, this modular parameter, is 1 over a complex prime. Okay. Good. So yeah, to conclude, I mean, I should say we did a whole bunch of other fun things with these. So you can really think of these partition functions. They're a little bit like baby CFTs. Okay, they're a partition function. They have an inversion symmetry. You could maybe think of these coefficients as a little bit like some spectrum of scaling dimensions. You can bootstrap them. You can average over them. There are a lot of fun things you can do that you can read about in our papers. So the conclusions are that the phase space of semi-classical gravity simplifies close to space-like singularities. There's an emergent SL2Z symmetry at each point in space for 4D gravity. So the Wheeler-DeWitt wave functions are automorphic forms and can be written in terms of L functions. And these L functions suggest a kind of DS-CFT type dual perspective on the singularity as some kind of Primon gas partition function. Long-term hope here is that in a setting where there exists a microscopic completion of the theory, for example, M theory or string theory, so that this BKL in 11-dimensional supergravity or 10-dimensional, for example, might also have a similar dual partition Primon gas partition function, might be interacting because the octonions don't commute, so it's more complicated what you mean by a prime number. And that the modular symmetries of this partition function might somehow guide the incorporation of quantum stringing effects at the singularity, i.e. the BKL dynamics, these symmetries could be a framework for a microscopic holography. Right. Thanks for listening.
Yes. So suppose I turn on like another field profile that can like fall in and couple to the gravitational BKL dynamics. Do you have a sense of how stable these modular structures are to like coupling with other degrees of freedom?
So I think that is about what about other matter fields, right? I think is what you asked, yeah. So if you're allowed to do anything, the simplest thing that will happen, right, very good, is that you'll get out, right. So say you're in 4D gravity and just add another scalar field, right? That adds another degree of freedom to the billiards, but it doesn't add another wall. And so the billiards will just, you don't have this chaotic structure, you just end up in some asymptotically Kasner regime without the bounces, right? So certainly that will, if you just write down some generic matter content, that's going to happen. That said, as I mentioned, for theories that you might care about, such as supergravity theories, you typically do get some interesting billiard structures, right? Good. So for example, for pure gravity is chaotic up to 10 dimensions, and in 11 dimensions and above, because there's a balance, right? You have the higher you go in dimensions, you have more degrees of freedom. You also get more walls, but they're not in one-to-one correspondence. And in 11 and above, pure gravity is not chaotic. However, if in 11 dimensions you add the 3 form of supergravity, then it is chaotic again, and you do get these modular structures. So it's not that you're always going to get the modular structures, but interesting theories seem to have them.
A spherically symmetric situation.
So
if I restrict to a spherically symmetric situation, how much of this chaotic dynamics survive?
Spherically symmetric depends on your matter content, right? So can we do planar symmetric? Is that just good? So I mean, so generically it won't, right? Right, good. So where do these walls come from? The walls come from 2 places, right? They come from this term, which certainly needs you to break, right? You need to have curvatures. So homogeneous models don't have this term, okay? But the walls also come from these terms, which are the momenta of these off-diagonal modes, okay? These are called symmetry walls. These are called curvature walls. When you have magnetic fields, they're a bit like off-diagonal modes, and you also get these forms. So typically with planar symmetry, you will not get this dynamics. What we did in this paper was cook up a model where you can, right? Because planar symmetry is nice because you can have ODEs and just solve things explicitly, but it won't be generic with that symmetry. Yeah.
Is there a particular linear combination of these wave functions which you could guess as some state of the singularity?
Yeah, that's very excellent. Yes, probably yes. I mean, okay, good. So obviously, firstly, you can get any classical solution by building wave packets from them, obviously, right? Because there is a sort of Hartnoll-Hawking, like there is a. You can try to make a Hartnoll-Hawking type state, and it's very uniform. So I mean, this is an ergodic system, right? And so, in fact, what you get at late times is a very uniform distribution. It's a finite volume space, right? And so the answer is yes, probably there is. If we hadn't been so distracted by all these prime numbers, we might have thought about it. But yeah, I think there is a candidate Hartnoll-Hawking-like states.
It's a uniform wave function.
Well, yes, right. I mean, actually, the interesting thing about this, you write down this Hartnoll-Hawking state even away from this late time limit. Sorry, very good. In the mini superspace models, of course, right? So actually, I should make this statement more generally. The literature in this, there's like a split, right? So at the same time as BKL, there's also Misner, who studied this Bianchi 9 model, which has a lot of these chaotic features, but is homogeneous in space. It doesn't have this decoupling of points. So within those mini superspace models is where people have thought about Hartnoll-Hawking type setups. But it might be more difficult outside of that.
The mathematicians seem to get also a kind of weak null singularity. Do you know if the BKL behavior is still?
No, that should be different, but also very, very interesting.
Is there any reason to think that vacuum polarization effects are subdominant to the dynamics that you're looking at?
So you mean quantum?
If we just put in the vacuum fluctuations, we have some very strong polarization effects. Maybe an effective description is higher curvature terms in the action, would that just completely change the picture?
That's an interesting question. I don't know. Well, so of course, eventually, definitely, all these high derivative terms and everything are going to be important, and that's where you might want to be in M theory or something before you ask this question, right? So that you know you're in a controlled quantum theory. And so Nikolai has thought a little bit about this, but I think it's not. We don't know. Yeah.
Get into that deep into the unknown territory, we might know enough about quantum field theory and curved spacetime to say that you're already encountering strong modifications.
Yeah, I think it should be an interesting question, which again, outside of some mini superspace models, has not really been looked at. And actually, one thing that is might be interesting, for example, the pi's, these theta degrees of freedom, their momentum drops out, which suggests that there might be quite strong quantum. Yeah, I think it's a very interesting question.
Yeah. So now that we have all these wave functions for this problem, what are some interesting questions we could ask about quantum gravity with this?
Right. Well, you could start calculating expectation values, right? I mean, I'm not sure. I think prior, but indeed, again, that's how much of a detour you want to go on first. Because I think there are things that they're more. You want to understand the wave functions a bit better first, but eventually, I mean, you want to calculate the expectation value of the volume of space as a function, or the expectation values of certain quantities as a function of the volume, for example. Yeah. So, for example, even semi-classically, as I was just saying, the fact that this region is compact means that you can write down a semi-classical wave function that's spread out over this whole domain. I don't know what kind of space-time that corresponds to. Maybe it's regular in some sense. Yeah.
Very naive question. So if you so this relation with the zeta function, is there an interpretation of the Riemann, the zeta, the Riemann hypothesis in the singularity?
That's right. Not directly, and not that, but indeed. So I think Bernard Julia was hoping to get some insight onto the Riemann hypothesis when he did this. I don't think he did in the end. But I can tell you. So what's pretty interesting. So the data in these, right? So to every state, there's a set of zeros, right? And there's a relationship between. So one way to specify the state is in terms of all of these angles, these angles, but equivalently, the information is all in the zeros as well. And there's this explicit, it's almost like a Fourier transform. There's this explicit formula that would let you write sort of sums over primes in terms of sums over these zeros. So they're definitely there, and you can do mathematical things with them. Let me just tell you one thing. So as you know, the wave function, the Mellin transform, what you get is the L function along the line. So in fact, this wave, the Mellin transform wave function has zeros precisely at the non-trivial zeros. So the way they show up most directly is the zeros of the Wheeler-DeWitt wave function in this basis. I don't know what to do with that fact, but you can really, yeah. I normally have a slide that I took out. Yeah.
Elsewhere, that doesn't show up.
Yeah, exactly. Yeah.
I think in the interest of lunch, let's thank the speakers.